Morning. All right, I worry that today we may have students attend in class or online. So if you are online, I posted your Flickr link online. You can answer the question by pointing to the right voice. I was wondering how many of us have finished the pre-test. Pre-test basically is a way to measure how much we understand at the beginning of the semester. And there will be a post-test in April, which measure how much we know after one semester of study. So this is essentially a survey question. One student in class, two students online. I should have 9 answers total. Anyone that didn't answer, please. Did you guys already
I
ask?
still don't have room.
Oh, yeah. Your name is
Alexis Val.
Alexis. Okay, I should give you the link last time. I think I have paper. Let me find out your number. Thank you. Okay. 6. Alexis, right?
Yes.
This is one of the students that's already withdraw, so I'm changing this to that your right last name is give you a card number 6. Sorry. All right. So this is today's practice attendance question. So I'm trying to figure out how many of us have did pre-class. Is your Georgia view already set
Yeah,
up?
I just got it.
Below to the corner. Okay. All right, so if your answers recorded, you should see your name highlighted. I think that should be everyone. And let's see. Okay, we still have a few answers that's no. You well, I should mention where you can find it. It's due tomorrow, so that's why I tried to mention it now. So if you want, I'm giving extra credit. So if you want extra credit, you should still do it. And it's course tools under review course tools, and then you click on quizzes, and you should be able to see the link. That's where you see the assessment pretest. The term assessment is to assess the efficiency of the class. So essentially, it's a data collection process. It also be a way for you to kind of figure out how much you know at the beginning of semester. I know many of you have had pre-calculus. So in pre-calculus, there may be a little bit something you can know about calculus, or maybe you already have calculus in high school. So this kind of measure where you are before you take this class. The end of semester in April, there will be a post-test, which kind of measure, it's the same question. If you want to, you should take notes. So as you were taking the test, if you take notes, you will find out in April, there will be like almost identical tests. where you're gonna compare how much you know, like what you don't know in the pre-test, you probably have some more ideas when you're doing the post-test. And we're using the same test to measure how much we have grown, how much we know more about calculus. Right? If you haven't tried it yet, please take the pre-test so we have enough data. Right now it was the one that took the pre-test. The score doesn't matter what, because it's after all before you take calculus. The test really will show how much we don't know, so it's okay if you. And I think the grade, the test grade, the pre-test test grade will be hidden from you, so you won't know what you score anyway. The point is to take it and try your best. This is 7 for A and it's 4 for B. So like I guess majority of us have taken it, and that's for today's attendance. Do you have any question from the homework? Yes, okay. Let me pull the homework link up. You can also bookmark the homework so you don't have to always go back to Georgia View. I put it in Georgia View because that way you can go to it if you have your Georgia View account. But this website is independent and you can actually bookmark this and try to take it once in a while when you have time. I went to my instructor account. Maybe I should try from the student side. I made a fake student account to kind of see what it shows on the student side. And that kind of shows that I forget to assign 1.5. Right, last week we did mention, we did started continuity, but I forget to assign. All right. Your questions about 1.2. 1.2. 1 and 2. Question 1 and 2. All right. This one, I felt like we talked about this last Thursday, right? It's fine. So the process is try to figure out what was the process to prove the limit of root of x if x is closer to 4, then root of x is closer to 2. So essentially, this is the process trying to prove limit of the root function. But when you were trying to search for the right boundary, you work out the algebra that allows you to put a proper boundary onto x minus 4. Right, so this is to prove the limit of root of x equal to 2 if x is approaching 4. So computation-wise, if you plug in 4 to root of x and root of 4 is 2. But the calculation is different than the mathematical proof. The calculation looks like, hey, you're just plugging in substitution, but limit calculation is not substitution. Limit calculation is to understand the process. If x is getting closer to 4, does root of x getting closer to 2? So we're trying to mimic that process if x is getting closer to 2, when x is getting closer to 4. So how do we prove that? Choose any epsilon, that's supposed to be the epsilon. Choose any epsilon, then we can choose proper delta. Whenever x is closer to 4 by delta distance, then root of x is closer to 2 by epsilon distance. So whatever. So epsilon is an arbitrary choice. In this example, we're choosing epsilon to be 0.6. We're proving that we're able to find a number whenever x is minus 4 is closer or smaller than that number, then root of x and 2 are closer than epsilon. So our target is to make possible that root of x minus 2 is less than 0.6. But you're going to try to figure out if we are trying to make that to be true, then what is x minus 4 is a proper boundary. So you have a boundary of 0.6 for root of x minus 2's absolute value, and you're trying to search for a boundary for x minus 4's boundary. So we're gonna go from something that is independent inequality. If you try to look at these two inequality, root of x minus 2, absolute value less than 0.6 has only one variable. So that is an inequality that we're able to solve for the x. On the other hand, root of absolute value x minus 4 is less than delta. This inequality has two variables. One is the x is your actual function variable. The other one is delta. That's now, this looks like there's two letters. These two letters is two separate variables. One is the variable of your function. The other one is a variable boundary. And one we have to solve and the other one we don't have to solve. All right, so the process, think about the x as being an arbitrary number that we allow to change around a certain value, but the epsilon or the 0.6 and delta is something that we're trying to identify the true value. All right, so the process is we start with what we do have, the one we can solve, like this one. Right, start from something that you're capable to work out the algebra and leading to the one you don't have enough information for. So normally the mathematical process is start somewhere that is approachable and try to gradually work out the process, go to someone that's slightly difficult or that's actually your true target of the problem. All right, so we start from here, and then the first thing to do, remember, is to take out the absolute value, right? Remember, how do we take out the absolute value? You know how to remove the absolute value is simple. What will be the first thing? Yeah, the equality. The third part, yes. So we would take out, we would have a negative 0.6 and we would have a positive 0.6. So negative 0.6 is less than root of x minus 2 and less than positive 0.6. So that's how we write or expand the absolute value and remove the absolute value symbol. Now you have an inequality. It's called a composite inequality where you have three sides instead of just two sides. This kind of equally tend to be hard to solve if you have like x here, the x here. So you have multiple x that will cause equation to be difficult. In that time, we'll often solve one inequality and solve the other one. So we think of it as two separate inequality. But right now, there's only one x, and that's impossible to like zoom into the x value. All we have to do is try to work out the process, remove the two, remove the roots, and then you can have x by itself. So that's all because we have only one x. If there's a multiple x, the process is slightly different. What we're gonna do is we plus 2 on all three. And this will remove the minus 2. I mean, minus 2 plus 2, they're opposite. You often try inverse or reverse or opposite process to reverse some of the term that you wish to remove. So this get rid of the minus 2, and then we're gonna have 2.6 over here, and we're gonna have negative 0.6 plus 2 is positive 1.4. So that's the root of x by itself. Then we want to get rid of the root. Root is a inverse function for the square. Square root inverses. So we're gonna square all three, just cancel the roots. And that way, if you square root of x, you get x. If you square 2.6, it will be 2.6 squared. And over here, yes. All right, you're gonna have to turn off your mic because I can hear it if you don't have your mic silenced. All right, so this is the left and right boundary for the x value. And but we remember whatever we're trying to do, we have a goal. So our objective is to try to find out the absolute value of x minus 4. So right now, what we are getting to is the proper boundary for x. We're trying to find the boundary for x minus 4's absolute value. So first you have to take x and then minus 4. So we're gonna have minus 4 on all three. So we go minus 4 here and minus 4 here and then minus 4 there. That way we'll have the left boundary and the right boundary for x minus 4. And of course, so this is gonna look like this, x minus 4 is less than. And you're gonna use your calculator on that, but for now, I will leave it like that because I don't want to go back to the calculator just yet. This is gonna be 1.4 squared minus 4. As you can see, the x minus 4 have a absolute boundary, which is the negative boundary. 1.4 minus 4 is negative, and 2.2 squared minus 4 is positive. There's a negative boundary, there's a positive boundary. However, we're trying to find out the boundary for x minus 4's absolute value. So now we're going to take absolute value. Right, and that's something that won't be automatically true because if you put absolute value, or naturally you can have this. So the absolute value of x minus 4 is less than this, but this is also bounded by that number, and this number is negative, so you have a negative and a positive, and when you put an absolute value, so the absolute value of this have this, the other number that we should take absolute 4, right? So now you have to ask yourself, do I choose this one? Or do I choose the right one, left one, or right one? And the answer is whichever is smaller. So this one or that one, the smaller one of the two should be the proper boundary for x minus 4, or should be the delta. So to answer the question, I think I have to calculate them. And I believe x minus 4 and x 1.4 squared minus 4 is smaller than the 2.6 squared minus 4, right? The absolute value. So we're gonna answer the 1.4 squared minus 4, and we know that's negative. You have to make it positive, or you can just do absolute value of 1.4 squared minus 4. Let's see if that worked. ABS stands for absolute value. If you don't want to use that, there's a keyboard that you let look like the absolute value symbol. I think that also works for absolute value of a number. Okay, so that will be the answer. Essentially, the answer is supposed to be 2.04. I use WebWorks allow you to enter the formula as long as it's all numbers, and it does the calculation of those numbers for you. So the answer for this question is 2.04. Does that answer your question? Okay, so that was question 1. And question 2, I think we haven't done it yet. It is a similar process. What we're going to do, we'll start over here, and that's what you are trying to do, and you want to maneuver the x minus 1.3 to be less than a certain number delta in order for 1 over x squared minus 1 over 1.3 squared to be less than 0.9. But in order to achieve this, you see this inequality has only one x. So it's possible to solve the x value from this inequality. And then once you solve the x value, being this is it's not an equation, it's an inequality. So your answer will be an inequality. So that will give you the boundary for x. And then you're going to go back, find the boundary for x minus 3, and then take the x value that gives you the delta. So the process is similar. If you want to see the process, so we'll do the calculation. And this time, since we've done a couple of times, I'll do a little bit faster. So you're going to start from here. And first we remove absolute value. You have 1 over x squared minus 1 over 1.3 squared, which is less than the positive 0.9. And bigger than the negative 0.9, right? And then the whole thing is trying to get the x by itself. So the minus 1.3 squared, that is essentially a number, so I want to get rid of the whole thing. And now it has no x value, so I'm going to plus, I will add, because that was a minus, so I'm add 1 over 1.3 squared. That way the x, the whole minus part will be going away. So plus 1 over 1.3 squared. If you have your calculator, you probably will be able to calculate the entire thing. That way there will be less writing. Right now there's more writing, but less time spent on doing the calculator. So that's the right boundary. This is left boundary. After you've done that, after the summation, you have 1 over x squared is less than. Over here is 0.9 plus 1 over 1.3 squared That's the right boundary. And the left boundary is negative 0.9 plus 1/1.3 squared. So here we have to look through, there's a square that I have to remove, and remember square is supposed to be positive. So 1/x squared is supposed to be a positive number. 0.9 plus 1.3 squared is also a positive number. And the question is whether this side is positive. If this side is negative, there's no need to worry about it, right? Positive number bigger than negative number is always true. If something is always true, then we don't have to solve it because it's true for any x value, therefore x. We don't have to worry about having the x within the certain boundary. But if this is a positive, then we have to worry about all of them. So we have to grab our calculator. The sum. What is it? Is this negative? You guys know? Is this negative or positive? It's a negative. It's negative. Okay, so the 0.9 is the 0.9 is bigger than 1.3 squared. Yeah. Have you tried? Okay, I'll calculate it. Because in my head I'm not sure. Negative 0.9 plus 1/1.3 square. It is negative. Okay, so that was negative, and then so this essentially this side essentially is negative 308, and a positive number bigger than negative number is naturally true. Therefore, we don't have to worry about this side. I mean, this is always true, but this is not always true. So then the equality we will continue on calculating is only the right half of the equality. The left half of the equality is all real, right? All x values satisfy the left side, and the right side is the one we're solving. So first thing you do is we can take the reciprocal, yeah? We can reciprocal. So we're gonna grab the 1/x, and we're gonna reciprocal that. 1/x will become x squared. 1/x squared become x squared over 1. So from that we get the x squared. X squared is bigger than 1/. Guess I should try to calculate that one, because keep writing it looks get bigger. 1/1.3 squared. Calculating this 0.9 plus 1/1.3 squared, and that would be this number. Okay, so that number belongs to the denominator. Oh, nothing there. I thought I copied that 1/. Too big. Right, so this is the 1.49, the whole summation part, and then you have reciprocal the left side, so you have to reciprocal the right side. Remember, reciprocal switch direction. 2 is less than 3, but 1/2 is bigger than 1/3. So reciprocal always switch your direction. 1/x squared is less than this number, therefore x squared will be bigger than 1/. Switch this one, and we opposite. Switch there. Are we okay so far? All right, so now we have a boundary for x squared, and then following that, this is how we work with inequality. Following that, what will happen is we're gonna take square root of it. And remember, square root of x squared is x, you might think, but actually x squared, this x can be positive or negative. So x squared, the x can be positive or negative. Therefore, the root of x squared can be positive or negative, right? We're thinking x is a large number. It can be a positive large or negative large. So we would, instead of have x, take root of the left side, we will have root of the absolute value of x. And then take root of the right side, we'll have root of the 1/. And that's a lot to write. It's nice to have that. I'll beat over. So that's the boundary for absolute value of x. But the thing is, we're trying to find the boundary for x minus 1/3. So absolute value will be kind of in the way. And as we mentioned, the x can be positive x or negative x. Now, if x is positive, then x is bigger than this number. I should really calculate it because otherwise I'll end up copying it. So it's actually square root of 1 over. All right, and then this number is that. So we know whatever on the right side of the equation actually is this number. That's the square root of 1 over 1.9171. So that means x got to be. So that now that we know the value, it won't do. Write it there. So for one possibility is, okay, so if absolute value of x is bigger than this, either positive x is bigger than this or x is less than the negative, right? So that is what we mentioned last time. If you have a absolute value of a number bigger than, let's say, 9, and then absolute value of x bigger than number, what happened is that this x is going to be really large. So x is either in here or this is -9. X can be also be here, like -10, -11. So x can be positive large or negative large, and that's the reason why when the absolute value of x is bigger than a number, then x is either larger than 9 or x is less than -9. This will be the process for removing absolute value sign if it's larger than. Okay. Before we're talking like if absolute value is less than a number, then it's less than the positive 0.9, bigger than the negative 0.9. But if you have x is bigger than a number instead of less than a number, if it's bigger than the number, then you have to kind of break down to the positive part and the negative, right? Okay, so I'm just thinking about removing the absolute value sign in the absolute value of x bigger than 0.8187. So after removing it, we will have on one side of the positive side or on the negative side, we'll have x is less than negative 0.8186. Okay, so why do we do this? Because we want to get x minus 1.3. If you want to get x minus 1.3, you have to have like a clean x. There's no square and there's no absolute value. There's no 1 over. You're going to get x bounded by something. So x is bigger than this or x is less than this. So pure boundary for x. Then we're going to minus 1.3. This will become, we're going to work over here. This will become 2 inequality. So you're gonna minus 1.3. We're trying to find boundary for x minus 3. X minus 1.3 is boundary. So we're gonna minus 1.3 this and this. We're gonna also minus 1.3 on both sides of this inequality. That's that's how it looks like. So then I'm going to take absolute value. Remember, we're trying to look for the boundary for absolute value, x minus 3. So you're going to take absolute value here, and you're going to have this boundary. If you take absolute value of x minus 1.3 here, and then you're going to have this absolute value. So essentially, we're going to find a 2 boundary. From this one, and you add absolute value, you're going to have x minus 1.3. That was that boundary. And then this boundary is going to be absolute value of 0.81876 minus 1.3. So that will be the boundary for this, right? Are you okay? On the other side, this, if you take absolute value, and then you're going to have this boundary. But because they are both negative, this one definitely going to have a bigger absolute value after you take absolute value. So I believe that one should be it. Does that answer your question? It said essentially this inequality provide one boundary for x value of x minus 1.3. this one, the second inequality provide another boundary. Whichever is smaller should be the boundary that we're shooting. Question? We okay? All right, so we're gonna take that boundary for our delta. The answer would be absolute value of, I'm gonna use AB as absolute value of, to have that, okay, the number minus 1.3. And that's what I was writing over here. This one, remember the minus 1.3. My writing looks not very clear, but it's 0.81876 minus 1.3 absolute value. And taken absolute value. So that's the answer for question 2. So the algebra is slightly different because we have this reciprocal 1 over is a reciprocal taken over the x squared. So it looks a little bit lengthy. Does that answer your question? Any other questions? All right, please try it. I looked over all of your progress so far. Most of you have done the assignment 1.1, 1.1 pretty much done. It's actually close right now. Right now, today is the due date for 1.3. And this one, most of you have done it. Maybe there's 1 or 2 students still working on it. Alexis, if you need more time, I'll open up the 1.1. Did you finish?
Yes.
You already did 1 point? Great. So what work was okay when you were studying? Okay. So basically 1.3 is due today. If you haven't finished yet, you should try to finish it. But I did see many of you have done the 1.3, have finished the all the question in there. But there's very little progress on 1.2. Or 1.4 or 1.5. So if you're a little bit behind on 1.2, try start it. If you see any question, any difficulty with any of the question, you can always bring that up during class. We'll talk about any question before we start anything new each day. Any question? So that's pretty much what we have so far. Okay, as you can see, this is pretty much all the sections on chapter 1. If we have anything sections left over in chapter 1, they were try to go over all the sections before we have test 1. Test 1 will be over chapter 1, which is mainly about limit. So, and we went over the first section. Section 1 introduced the informal definition of limit and focused on the calculation. I started 1.3 after section 1. Section 1 introduced calculating limit numerically or graphically. In 1.3, we talk about calculating limit value analytically, try to use a couple of algebraic methods to simplify the limit calculation. And then eventually we can calculate limit using substitution after we're removing any problem in the calculation. And then 1.2, we worked on a formal definition of the limit equation, limit symbol, and how do we go about proving a mathematical limit. So that's 1.2. 1.4, we talk about one-sided limit. Essentially, a limit is a process of trying to find the tendency of a function's change, a function's value. So for any function, you have an input, you have an output. The input value, when you try to present a graph, the input value is on the horizontal axis and the output value is on the vertical axis, which is why most of the time function graph will be a 2-dimensional picture. And therefore you can figure out the limit using the picture. With one-sided limit on the horizontal axis, on your x-axis or on your number line, if you identify the c, the value that x is approaching to, x can approach the value from the left side or from the right side. This is why we're able to define the one-sided limit and try to understand from the numerical side or from the formal limit definition side. So either way, we should be able to understand one-sided limit. 1.5, now that we have enough study or concept over limit, we can use limit as our definition for continuity. So by definition, we see a function is continuous at a point as long as the limit of the function at a point equal to the function value at that point. Basically, continuity means the process and the individual values, the global behavior and the local behavior is consistent, then that will be continuity. Another way to see is basically continuity allows the function to be one single pass going through the entire interval. So that's 1.5. And then we have two more sections left in this section, the special kind of limit. 1.6 is infinity limit. So far we're trying to allow x to go to a finite number, and then the limit value, if they exist, it will also be a finite number. So we have finite number, and we haven't really touched on the idea of infinity. So 1.6 focus on if x goes to infinity, what will happen? Now, if y goes to infinity, what will happen? So 1.6 we study specifically if infinity is involved in the whole picture, how we study it. 1.6 is limit at infinity. I guess these two are similar. All right, let me pull up my file that I had before and so it's 1.6. That's the one. There's 1.6. Let's talk about infinity limit. This one is when the function value goes to infinity. Limit involving infinity. Okay, so when we have infinity, we have already seen a couple of scenarios that is in this question. You see a reciprocal relation, and we're trying to pair the understanding of infinity with graph of the function, because visually it makes more sense once you combine that with numerical understanding. So over here on the right side, you have limit of 1 over x squared if x is approaching 0 equal to infinity. Okay, visually it is, right? X is approaching 0. So on the x-axis, you're going to find 0 right in the middle. That's when x equal to 0. If x equal to 0, you see, you go up to the picture. This is the graph of y equal to 1 over x squared. You can see there's nothing. There's no function value matched when x equal to 0. And we know why that's the case, because if x equal to 0, 1 over 0 squared will be undefined. Undefined value had no corresponding point on the graph. That's why it's empty. So you can think of x equal to 0 as an invisible wall that will separate the entire function graph into two parts, left part and the right part. So the function y equal to 1 over x squared is being defined with a single equation, but the visual graph actually have two separate parts because the definition of the function causes the function to be undefined at a given point. So let me use a different color. So y equal to 1 over x squared will be our function, or that will be the correspondence between the x value and the y value. As you can see, if x equal to 0, it will be undefined, so there's no y value corresponding to x equal to 0. So we will have to artificially define by the definition of the function. We know that the x is now going to be in the domain. So in this function, the interval of continuity or domain of the function will be negative infinity to 0. This is open, and then you start from 0 to positive infinity. So essentially, this is one single point that's taken out of the entire number line. 0 is not included in here. So 0, smaller than 0 is negative infinity to 0. That's just notation. So this is the interval notation. Right? This interval notation essentially means x is less than 0. Right, this notation is interval notation for x is bigger than 0. Okay, so for this function, x can be bigger than 0, x can be smaller than 0, x just cannot equal to 0 because it will be undefined. All right, so as the result, the consequence of these is that the domain of this function is two separate parts. The positive part and negative part. And that's why the graph of this function has two separate parts. The negative part and the positive part. So it's two separate parts. So that makes us zero is very interesting or very important part of the entire graph. Around zero, behave the function become really, really different than all the other points. So for example, 0.5, if x is 0.5, 1 over 0.5 squared would be 4. So over here, the y value there should be a 4. So for any other point, you can basically calculate it using substitution, but at zero, also when x approaching zero, the function of y seems to be get bigger and bigger. And that's why we say if x approaching zero, then 1 over x is actually approaching a really large number. For example, we can try and remember in section 1, if we want to see what happened if x is approaching zero, we can try numbers such as 0.1, 0.01. We're getting closer and closer to zero, or 0.001. And we're going to watch what happened to 1 over x squared. Okay, so if x equal to 0.1, just 1 over 0.1 squared, so it's 1 over 0.001. So then the answer would be 100. All right, so if x equal to 0.01, and turns out this is gonna be 1,000. Right, and then if x equal to 0.001, this is gonna be 1,000,000. Right, so you can see as we make x smaller and smaller, 1 over x is getting bigger and bigger, and that's the reason we say limit of 1 over x squared actually equal to infinity. So 1 over x squared is not equal to 1,000 or 100 or 1,000,000. It equal to infinity because it never stops at any value as we make x closer and closer. You can make x equal to 0.0001. You're going to see 1 over x squared is getting even bigger. So what makes more sense is to identify that this can be arbitrarily large. You can make x even closer, and you can make 1 over x squared even bigger. There's no boundary for how big 1 over x squared can be. That's why we say it's infinity. There's no meaningful boundary, and now we define this artificial boundary for something that is going up, 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 up when there's no boundary. So you see here this. So what we are doing, I did a positive number, so we're actually mimicking what happened here. Just increasing without boundary as x goes closer and closer. So when we are moving along the curve from, see, we're getting closer to zero from the positive side. And then it looks like the y value is increasing, keep increasing. And that's why we see it's infinity. Same thing happened if you make x equal to a number negative, but closer to zero. It will go also up because the square, there's a square. So if you square any number, it makes it positive. That's why 1 over x squared will always be positive. And you have a positive infinity on the left, and you have positive infinity on the right. The entire thing. It's infinity. Any question? So that's 1, right? This limit is when it shows a relation between the value and the reciprocal. 1 over x squared is reciprocal of x squared. So x gets smaller and smaller. X squared gets smaller and smaller. 1 over x gets bigger and bigger. So there are reciprocal relation between a number and its reciprocal as infinity. So this is the equation, limit calculation that involve infinity for the y value. So as a consequence, the whole limit goes to infinity. All right. On the other hand, at the bottom one, you see there's a special thing that says if x goes to infinity, what happened to 1 over x squared? So how do we go about understand that kind of situation? The second limit equation indicating that similar reciprocal relation, that is x is approaching infinity. In this case, we are identifying differentiating infinity from negative infinity. On the number line, if x is really, really large, like over here, right? And then if x is a positively large number, we see x is approaching positive infinity. If x is negative large, we see x is approaching negative infinity. So infinity and negative infinity are different. in this case, x is approaching positive infinity. And when you see x approach positive infinity, that is x is taking on a really, really large number on the right side of the number line. So if we want to understand this limit with numerical calculation, I guess I could also set up a table. So in this case, we can do something that shows when x is approaching larger number, what will happen to 1 over x squared. For example, large x value, you can say x equal to 1,000 is a large number. So this will be like 1 over 1,000 squared, which essentially is a million. A million in the denominator. So 1 over a million, which then equal to 0.000. I mean, you can use your calculator to calculate it. It's going to be 0.000001. So it's a really small number. Yes, that's a little very large already. If x equal to a million, I'm trying to make it bigger, then what will happen 1 over x squared? It's going to be 1 over 10 to the power 6 squared. I guess square should be in the denominator, but it's the same. This is going to be 10 to the negative 12 power. And 10 to the negative 12, you also see the same thing on your calculator if you do it with your calculator. 10 to the negative 12 is a really small number. It's 0.000000001. Basically, you have 12 zero before the 1 after the decimal point. So you're going to see a lot of 0 before the 1, which means it's a really small number. So essentially, what we're indicating is that if x takes out a really large number, 1 over x squared takes out a really small number, essentially it's almost 0. I mean, if it's 0.0000001, of course, that's really small. But you can make it as small as possible. You can make it even smaller by taking even bigger x value. And that process is indicating x get bigger. 1 over x squared just gets smaller and smaller. And we see that limit is essentially 0. So this is how we understand the limit involving infinity using numerical exploration. Try different number to see the tendency. Any question? So as far as the infinity, I often try numbers because that's what's giving me the idea. If we try to look at the theoretical foundation of it, you can also see from the reciprocal standpoint. So if you think of it, you can think of it this way. Basically, if x is approaching infinity, meaning x is a really large positive number, then 1 over x will be approaching 0. With the reciprocal number, if the number is bigger, then the reciprocal is small. If the number is small, the reciprocal is bigger because they're really basically approaching two separate directions. And then what happened to 1 over x squared? If 1 over x is approaching 0, 1 over x squared also is approaching 0. Because 1 over x squared is a square of 1 over x. Basically, you square this, and then you're going to get this. Essentially, it's a square relation between the two. So that's how I would approach a problem from an analytical standpoint. Just look at what will happen when 1 goes this, what's the middle, what is the F1? So it goes slowly from one variable to a small formula to a slightly bigger formula. So we can gradually see the process. Any question? Right. I hope that start our thinking process about limit calculation involve infinity. All right, so this is another question. We're trying to find the limit of 1 over x minus 1 squared if x is approaching 1. So here the graph is already provided. It says find the limit, and using the figure that we have here, it's a figure of y equal to 1 over x minus 1 squared. You can see what happened here is this is a 1. X equal to 1. Then 1 minus 1 is 0, so x equal to 1 is an undefined point. x equal to 1 can be in the domain because if x equal to 1 will be undefined. So the domain for this function is negative infinity to 1, 1 not included, and then 1 to infinity, right? And the question for the limit, you see the graph, if x is approaching 1, what happened to the y value? It went up, right?
Mhm.
So the limit is, what's the limit? Infinity. It's positive infinity. So if we try to write it out, we should see a conclusion like this. Limit of this function is equal to infinity. So that will be the conclusion for this question. You can also try number, and it says that x is approaching 1. You can make x equal to 1.01. So you can try and calculate 1 over 1.01 minus 1, and then square. Okay, and then 1.01 minus 1, 0.01, and then square, which then equal to 1 over 0.0001. Then finish the division, you get 10,000. So that's one calculation. Of course, trying one calculation does not show the entire tendency. You can also try 1.001, and you can see the answer is going to be a million. So as you were getting x to be closer and closer to 1, it illustrates the whole thing is getting bigger. And that's kind of verify our perception that the limit value actually equal to infinity. Any question? Seeing that allows us to say that we get a answer that's a large number. And that's indicating limit equal to infinity. This is another question. All right, the question says, let's find the limit of 1 over x when x is approaching 0. Okay, so what we see over here is this. Right, so then here we have a slight problem because when x is approaching a finite number, it can only approach that number from left side and right side. However, before you can see this one, the bottom one, if x is approaching positive infinity, that is the right side. As far as infinity, you have the positive infinity is the right end of your number line. The negative infinity is your left end of number line. You can approach the negative infinity only from the right. You can only approach the positive infinity only from the left. Therefore, that's only one-sided in a way. But when you have x approaching a 0, 0 is a point on the number line. So you can go to 0 from the left, just like this, or you can approach 0 from the right. And you see what happened there, and they're not going to the same direction on the left. And when it's like this, x equal to 0 become a wall, like negative infinity to 0. You gotta stop there because you can't pass through. And then there's a 0 to infinity. If you try to get closer to 0. It's like you're driving along the curve, and then this is like the wall that don't allow you to pass. And then as you're gonna have to turn around and go up here, but when you're here, you have to. So this is like a pass that we can drive the car over, and then having two separate direction. Over here is down, over here is up. So we can see even from the graphic display that the limit seems to be approaching two different direction on the left and on the right. So we see that, well, let me try to write the left side and right side with two separate limit notation. Remember, we set a one-sided limit. So if we want to know this two-sided limit, 1 over x when x approaching 0 from the left. All right, for the left limit, we use a little minus sign because it's a negative side of 0. So we're saying we're going to try to get closer to, this is 0, closer to 0 from the negative side, meaning that along the curve of approaching 0, this side. Right, you can see where we're going. So what should be the right limit here? If it's went down, how do we see it? negative, right? Negative infinity. So this is going to be saying that the y value is decreasing without bound. Basically, when the y value went down on the graph. On the other hand, the limit value of 1 over x when x is approaching 0 from the positive side. That means we're approaching 0 from the right side. This is the positive side. And you can see where everything is going. Okay, so what is the limit value? Positive infinity. So this is a limit involving infinity, and we see the y value going to positive infinity here, but we see the y value going to negative infinity there. So to answer the original question, what will happen if x approaches 0 with no positive or negative sign? When there is no sign for a finite number, we mean it could be left or could be to the right. It's possible. And therefore, because the two are not agreeing, the answer to the entire question would be limit for this. All right, and I'm going to say this is equal to, what should be the answer? Does not exist. Yes, the left side and right side is not equal, so it's D and E. I'm trying to use this example to illustrate that people often say when the limit equal to infinity, that also does not exist because we don't see a finite answer for the limit. But somehow when the limit equal to infinity is slightly different than D and E, and you can see the differences here. The two-sided limit, you can only say it's D and E because it's not infinity and it's not negative infinity. So there's a subtle difference between D and E and infinity. And the thing is, whenever the limit equal to infinity, we want to be able to see it and we want to be able to study it. That's why we invented the notion for infinity, because when the limit equal to positive infinity or negative infinity, it shows a tendency of the graph, right? And then to actually illustrate what's going on with function at 0, you actually need 1, 2, 3, all three of them. If you only have 1 or 2, it might not be sufficient. And for example, if you cover up the one-side limit, you see the limit D and E. And obviously that hides the reason why it's D and E or what will happen on the left and on the right side. So all two of them will be useful to study this function behavior around 0. This function is something that we might try in college algebra. This is called a rational function because we have a division, a number divided by the variable x. X is the denominator. So you can think of the numerator as polynomial with degree 0. Denominator is a polynomial with degree 1. So when one polynomial divided by another polynomial, we call that rational function. As in rational number is division between two integers. Rational function is division between two polynomials. So with rational function, we often see what people call asymptotes. And we should mention this asymptotes notion. And you hear that also in college algebra, when you look at the graph. And when you look at the graph, this invisible, the dashed line is x equal to 1. So x equal to 1 is called a vertical, you see the vertical line, it's called a vertical asymptote because you see a limit value that is approaching infinity. Whenever the y value is going to infinity, the y value is going to infinity. Whenever the y value is going to infinity, we have a vertical asymptote. So in this graph, the x equal to 0 is a vertical asymptote. Down here in the second inequality, it says when x approaches infinity, the y value goes to 0. So in this example, we see y that is finite, but we see that x is going to infinity. So x is going to infinity, but the y value is a finite value of 0. That is a horizontal asymptote. So whenever x is finite, y is infinity, that is a vertical asymptote. Whenever the y is finite, but the x is approaching infinity, that's a horizontal asymptote. So whenever you see that x equal to 0, x equal to 0 is a vertical asymptote. Y equal to 0 that's when x goes infinity. So y equal to 0 will be a horizontal asymptote. Horizontal asymptote. Visually, you can feel like you can see why we're talking about asymptotes. Asymptotes can become the guide for the whole entire graph. So for example, the y equal to 0 is like a bottom boundary for the entire picture. Though doesn't mean y equal to 0. It means y equal to 0 is something that the entire graph is infinitely trying to get closer to but never reach. Now, vertically, the x equal to 0 is kind of like a guide for this graph. You see, the y value is getting closer and closer and closer and closer to the line x equal to 0, the middle line, vertical line. But it will never get to it. So it's kind of guided what happened in the first quadrant and the second quadrant. You see this? They're getting closer. So knowing the asymptote allows the graph to be more accurate and allow us to study the function better. So for a rational function, we also want to know what is a horizontal asymptote and what is a vertical asymptote. Horizontal asymptote often affected by the domain is the domain infinity to 0, 0 to infinity. So obviously 0 is an asymptote. Horizontal asymptote is a horizontal line, therefore it's a y value, and that often is a y value limit for the entire function when x is approaching infinity. So for horizontal asymptote, our target is to study the behavior of the x on the further right or on the further left. In this graph, in this equality, we're talking about x going to the positive infinity. We're looking at what happened on the right side of the whole graph. So the horizontal asymptote essentially the left behavior and the right behavior for the entire graph. Try to combine our understanding of the numerical value and understanding of the graph, the entire thing. All right. This is the definition for vertical asymptote. If the limit of the f of x approaching c from either left or right is equal to infinity or negative infinity, we see the function has a vertical asymptote at the x value c. So a vertical asymptote is a vertical line. If it's a vertical line, of course, it's the x value. So vertical asymptote is a particular x value that causes the y value to go increasing without bound or decreasing without bound. Because whenever the y involve infinity and x involve a finite number, the x value is a vertical asymptote. Okay, so we occasionally will be asked to find the vertical asymptote. So this is enter a little bit of limit notion, but for the most part, is understanding vertical asymptote or horizontal asymptote of the rational function. So it's slightly related to what we were studying in pre-calculus. Right, this question is to find the vertical asymptote of this function. So what we can do is to going through a process to see how do we identify vertical asymptote. One thing we should remember, why do we have vertical asymptote? Vertical asymptote is one function like increasing without bound. Why do we have increasing without bound? Because we have division by 0. So we often have to focus on when you want to understand vertical asymptotes, you want to see when will we have a division by 0 situation. So the denominator will be what we are focusing. Whenever the denominator becomes 0, we often see a vertical asymptote. Of course, you should also confirm the limit with limit calculation. If the limit goes to infinity, you have vertical asymptote. If the limit is not infinity, we do not have vertical asymptote. I'm going to try to confirm this. The denominator can be factored. This is actually x squared minus 4, well, minus 2 squared. Try to confirm that we have a subtraction of square here, 2 squared. Okay, so remember, if you have 1 square minus another square, how do we factor it? Can we factor the denominator? So this is equal to what? What is it? You remember, a squared minus b squared is? No, it's not necessary. We're not talking about Pythagorean. We're talking about subtraction of square. Remember? Right. So equal to x plus 2. times x minus 2. I'm referring to the formula that we might mention before, that if you have a squared minus b squared, we're calling it the square difference. Subtract the two squares, so square difference. Whenever you have square difference, then you have this is equal to a plus b times a minus b. You can call this the square difference formula. Right. So applying that, which allows us to actually write the numerator is no change. Denominator become x minus the x plus 2 times x minus 2. Why do we factor? Because if you factor, you see two terms multiply each other. So you can easily see when would the denominator become 0. Because if the denominator equal to 0, and the numerator has no such factor, so there's no common factor between numerator and denominator. Therefore, if the denominator equal to 0, you see division by 0. For example, x plus 2. If x plus 2 equal to 0, x equal to negative 2. So negative 2 is 0 for the denominator. If x equal to negative 2, then the denominator equal to 0, because this is going to be 0 times negative 4. 0. And this is going to be 3 times negative 2, because x equal to negative 2. 3 times negative is negative 6. So entire thing will be negative 6 divided by 0. And that will be undefined. So negative 2 definitely is going to be a problem. If you look through the number line, this is negative 2. Another one will be x minus 2. If x minus 2 equal to 0, then 2x equal to 2. 2 minus 2 would be 0. And numerator is going to be 3 times 2, which is going to be 6. And that's no problem, but denominator equal to 0, numerator equal to 6. And 6 divided by 0 would be undefined, since the entire thing is a division. So we would know that 2 would also be a point that we should take away from the domain. So right now we see the domain of the function will be negative infinity to negative 2, and then negative 2 to 2, and then 2 to positive infinity. We just say this interval notation is guaranteed that x is not negative 2, x is not positive 2. But that's not the question. Answer to the question is the vertical asymptote, and the how do we see that vertical asymptote? There are two vertical lines, x equal to negative 2 and x equal to positive 2. That's how you see the vertical asymptote. It's supposed to be an equation of the x value. So these are the answers. The rest, I was just trying to go through the process. How do we know the asymptote is negative 2 and 2? Question. Right, so this is not a limit calculation. This is just to understand the vertical asymptote notion. We can also see how the asymptote is related to our graph. Let's look at one of these graphs. All right, so we're talking about this function y equal to 3x divided by x minus 2 times x plus 2. And the graph. So you can see the graph is being separated into 3 parts: the left, the middle, and the right. So what we're looking for is this invisible wall that separated all these graphs. We already determined those two. There were these two lines. The first one is x equal to negative 2, and the other one is x equal to positive 2. So x equal to negative 2 and x equal to positive 2 is the equation of the vertical asymptote. You can see on the left it went all the way down, on the right it went all the way up. And therefore at negative 2, there's no limit, but x is equal to negative seems to be this line that separates the entire graph into 3 separate parts. This is the x equal to positive 2. Any question? So just to try to use a graph to show that these two lines is a vertical asymptote. That put a vertical asymptote. This function file already have the graph in there. That's the graph for f of x equal to 3x over x squared minus 4, the same graph that I was showing on decimals. And, all right, we do have to watch out for the factorings. This is a similar example. We have x squared minus 1 over x minus 1. And we tried this before. The answer is x plus 1. If you divide x squared minus 1 over x plus 1, you're going to see this is a line, y equal to x plus 1. The reason that we don't see asymptote, see here, there's no asymptote. That's because if x approaching 1, okay, then you can see if x approach 1, see that's 2. So this limit is not infinity, right? Remember, the limit of the function has to equal to infinity for us to have an asymptote. In this function, the x minus 1 is a common factor. After we cancel the common factor, you see there's no division by 0 of a number. It is actually 0 divided by 0, right? The 0 can be canceled and there's no more 0. So the actual limit is 2. So at 1, it didn't go like this way or that way. That's why this function do not have a asymptote. It has no vertical asymptote. That's also because this one has a removable discontinuity. And this function, however, have a discontinuity that's not removable. So there are different discontinuity. If we think through compare the graph here, what we can see here is 3x over 3x over x squared minus 4, the graph that we had before. A simple change we'll see like y equal to like 2x over, I'm trying to show a similar example to x squared minus x squared minus 4. That's 2x. Okay, I'm trying to go by x minus 2 times. Okay, this is okay. So I'm trying to look at the difference between the two functions. The red one has two virtual asymptotes, one at the -2, one at the +2. Now the black one, the second function, x minus 2, and then here's x squared minus 4. X squared minus 4 is x minus 2 times x plus 2. So you can see the x minus 2 is being canceled. Therefore, for this function, x equal to 2 can be canceled. Therefore, 2 is not an asymptote. That was canceled. So then one of the discontinuity is removable. X equal to 2. See, that's a finite value. It has a limit. On the other hand, x equal to -2 are now being canceled. So at -2, you still have that vertical asymptote. So whichever is the asymptote really depend on the eventual limit value. When the limit approaching infinity, like this or this or this or this, we have a vertical asymptote. But if the limit is not infinity, like that's not infinity at 2, and therefore 2 is not a asymptote, but on the x equal to -2, we still have infinity. Is what we have the asymptote. So that's why limit calculation often helps when you want to identify the virtual asymptote. And it looks like the time's is up, and I should be posting the 1.6 assignment. In the meantime, please try to catch up with 1.2. 1.3 and 1.2 are few recent, so let's try to finish them before they're due. Thank you. That's it for today. It's okay. No problem. All right.